All right, so we're ready for the next speaker. It's really nice to have people from the university here, and I'm really curious about this talk because it's about evolutionary algorithms. And my background is actually from evolutionary biology, so I'm really keen to hear more about that. So Kyrre Glette here, he will tell us more about how evolutionary algorithms can be used as a design tool. Welcome.
Thank you, Jon. So yeah, as he said, I'm from the university, and these are things that I do in my work time. But as you might know, like at university, the division between work and spare time might get a little blurred at times. So it's something you do as a hobby as well. So I'm going to talk a bit about evolutionary algorithms and what we maybe could use that for. Some inspiration slide. I don't have like a colored pony, but I will start this one to draw your attention. So this one is actually made by a student of ours sitting in the room, Torjus. It's made based on the blueprint of a Dutch artist who has these massive beach walking creatures. And the reason I have this in the slide is that well, he has this very interesting mechanical linkage, but he optimized how to do like the exact sizes and so on of this using a kind of evolutionary algorithm. And you see here you have like a boom, it's called, for a satellite to kind of have some solar panels. And there have been some researchers doing evolutionary algorithms to optimize the shape of this from like this conventional design to an evolutionary design in order to reduce vibrations for this one. And here you have like a coffee table. So it was automatically designed and was produced and made its way into the living room of the designer. And finally you have this fantastic machine-designed antenna, which looks totally different from what an engineer would do, and it's actually made its way onto a spacecraft because its performance was actually better than what a human engineer made. So I think this is something that can be used for a like totally automated design process, but you can also use it as a kind of invention tool, as like an inspiration in your design process. So let's dive into the details. I won't go too far into the details, but this is what an evolutionary algorithm looks like. You start with just generating a lot of random solutions to your problem. And then, of course, some of them are really, really bad. They don't work at all. Some of them might work a little bit better. So what you do is actually to like then test all of them. And you find out like, well, maybe this solution actually works a little bit better than the other. And then so we throw away the bad solution and we try to make like new solutions based on these old, which are a little bit better than the totally crap ones. So you do this like a loop a lot of times, and eventually you'll find a quite good solution to your problem. And then you can like stop and use your solution, use your thing. If you did it in a computer, then you can actually make your thing to hardware. But there are a couple of like details you need to kind of take care of to make this possible. So the first thing is like you want to like make a coding for your solution. So I have this example of like we want to make some pictures. We want to make like art from this evolutionary design process. So we have like a picture here with like say X and Y coordinates, and we have a representation of our picture here. That's basically a tree, so it's coded in your computer, and it takes as input the X coordinate, the Y coordinate, and multiplies them together. And that's the result you get. And then you can like build on this tree to make more complex images. So that's your coding of the solution. And then you have to kind of need to know a bit like what are good solutions and what are not so good solutions. And you could actually specify this very like mathematically. You could like make a formula. You can have a simulation program that simulates the stress and vibrations of this satellite part, or you could also do it a bit more interactively, actually, because like if you have two pictures, like two art pieces, then it's really difficult to find a good formula for evaluating them. So what you could do is actually to use your own brain, or try to kind of make some AI that kind of then selects which one is better. And the third thing is that you need a way of doing kind of the really important part of this evolutionary process is that like good solutions need to transfer their kind of good features to the children, and you also need a little bit of variation so you can actually have improvements. So you get a little bit of code from your parents, a bit of zeros, a bit of ones in this case, but you also do a little bit of mutations so you can actually have some random changes. And of course, like lots of these changes, they make the solution worse. But that's not a problem because we just discard them and we keep the good ones. So once we've done sufficiently number of variations and selections of good and bad pictures, we can end up with a really like huge tree with codes for your solution, and then you evaluate that for the picture coordinates, and you can get a much more complex and interesting picture. And this is the result then of a school project actually with a guy called Erling Ellingsen. So we did this genetic art, and we're quite proud of the results. It's quite amazing what you can do from this evolutionary design process. So, well, that's 2D, it's in a computer, but we don't really have to stop there. So, of course, like that's a 2D formula, we just introduced X and Y into the algorithm. But it's very easy to just add another variable. You can add the Z dimension. And then you get the three-dimensional kind of formula, which can code for surfaces and so on. So I know a guy in the US. He did this actually in 3D before I got around to do that. I wanted to do it. But so if you go to this endlessforms.com, you can actually use the web interface there and generate new random solutions and select the ones you like and do mutations and so on. And you can get these 3D functions, which are then converted to triangle surfaces through like an algorithm, a triangularization algorithm called marching cubes. So then you can like download the 3D file, and of course you can then like make a solid object out of it. So that was the art. Now, what I'm doing most these days is actually to apply this to robotics. So, together with some students, we are doing this evolutionary design of robots. So we want actually to design not only the shape of the robot, but also like how it walks. And we think that like by taking those two things into account at the same time, there's like a chance that you could actually create a really like optimal solution in a way. So for the one on the left, that's like the initial design of a robot, and then we'll let the algorithm decide various parameters of the robot, like the length between the hinges, the length of the legs, and so on, and also like the way it is controlled, like the brains of each joint. And on the other one, we want it to be even a bit more flexible. So there we don't limit like the number of legs and joints in the same way, and it's possible to do even more flexible things. So Okay, that's good, but in order to like test all those solutions, you need to test like in your like one generation of this evolutionary algorithm, you need maybe 200, 300 robots to test. And then you need to run this for like say 1,000 generations to kind of like really explore the different solutions. So what we do then is actually to use freely available physics libraries like designed for games. And then we test our different solutions in the computer, and we use lots of computers to kind of test a lot of them in parallel. So this is what it looks like when we do one evaluation of one of these robot shapes. And then we can automatically like give it some values, some like this moved so far in so many seconds, and it has so and so much material, so like the weight isn't that good, and it's like so much different from the others, and so on. So I think actually now we do have a little bit of time, so I'll show this from a real program. If this might suffer from the demo effect, but let's see. Yeah, here we have it. So I can actually see that this is running now in real time, just one process on my computer. It's testing out a lot of different combinations of bodies and control systems at the same time. And well, it's the first generation. It doesn't really work that well yet. So if we let this run for like say a couple of hours, then you'll start to see that these robots are actually moving. But I think we don't wait for that now. So as we saw, this one was actually then one result of these 200 generations. And so we have like, we're at the 200th generation. We have like the final population of robots. And like we have some measures of like how good they are, but since we have like different objectives, we have like, we want them to be as small as possible. We also want them to be, that was like as small or as light as possible, but also like we want them to move as long as possible, as fast as possible. So we get like a lot of solutions which are kind of, one of the red dots is not better than any of the other red dots, it's just better in different ways. And then we can use those as like an input to like the final design decision. So we want like a little bit small robot, but also one that's performing good. Like we could take a trade-off in here, or we could like take the smallest possible. So, and then like once you selected your robot, we push a button in our system. Of course, we coded the algorithms to do this as well, but we generate a triangular mesh from it. So it's like a mix between models from SolidWorks that we modeled and generated shapes from these basic kind of building blocks. And then we 3D printed it. It's this is done on this Connex 500 printer, which we are like blessed or cursed with having. Okay, it's a little bit different robot being printed just now, but that's the time lapse I had available. And then in the end, we take the parts and assemble them with really like off-the-shelf servo motors, very easily to control, and we don't need any separate electronics to test it out, because we really want to like test a lot of different combinations. So this is one batch of solutions, where you can see like in the middle we have the human designed robot, and then top left we have a optimized robot from the process, which has then which is lighter, and bottom right we have a bigger robot which is faster. So we chose two different robots and tested them against the original one. you might see that this has a little face in the front, because we had it at the Maker Fair, and we didn't want to like scare the kids too much when it was moving, so that's why we put its face on. So well, maybe it's not that surprising. This one didn't have that much freedom to kind of change its shape. But for instance, with this big one, there was quite an interesting feature that we didn't think about in the beginning. So it has really large kind of front legs and smaller rear legs. So while it's kind of moving the front legs, it can also kind of move the rear legs under the front legs. So it can actually like take much bigger steps than you would like with a typical design. And here are 5 kind of different morphologies selected from the other process. And we can see that we get a little bit of different solutions. Like some of them are faster, some of them are lighter. So okay, now we have our produced robots. I can actually send around. And these are the result of computer simulations. But the thing is that like once you're doing a simulation, you cannot really 100% depict like the reality. And the evolution is a master at kind of finding holes in this simulation in a way. So like things are really not behaving always as you expect them to be. So these maybe have like a, say 50% performance loss when they're walking on the real surface, because like it's difficult to model friction and weights and all of that correctly. So what we're working with now is to kind of do like a real world adaptation process, and I'll show a little video of that. So here we have the robot in our studio, and it's you can see here that it has small dots, markers for a motion capture system, so we can know its position, how far it's moving. And this this cable here, it's quite interesting. We have that connected to a computer, but it's not as easy as that, because if the cable is too long, it will stumble in its own cable, and the process is broken. And if it's too short, then well, it will not be able to move freely. So to do a lot of kind of training and evaluations with this robot, we needed to kind of make this servo-controlled dispensing of cable system, which accords to like how far it's away, then it will give more cable to the robot. And you can see now when it gets a bit far away, you'll see an interesting thing. It was kind of dropping dead, and once again. That's because we had to also take into account that like the robot actually could tilt over and land on its back. And then when it lands on its back, it's kind of broken, or these balls might fall off and so on. So there are a lot of things to kind of think about before you get like a stable system. So what it's doing now is to kind of test its result from the simulation and try to improve on that. It's trying, and you can maybe see that it's probably like 4 seconds of each movement. It's testing and measuring the distance and doing kind of a new evolution on the real robot. So like some a bit more crawling strategies and so on. So that's where we are now, and we hope then to kind of get back to the performance we had in the simulator again. But of course, you don't have to do it as complex as we are doing. So I was hoping like that maybe some of you could get some inspiration. So I was really inspired by those strawberries today. And thinking that, well, maybe you could like just make some kind of robot from your strawberries, and you can use evolution as a kind of tool to make it walk in a way or the other, because you don't really know exactly how this is going to work. And there was actually some researchers doing something similar a while back. So they just built a random kind of servo and stick robot, and they applied this genetic algorithm, and they made it walk. So I think like one easy way to start doing that, you could like put an LED on your robot, and then you could have like a camera or a Wiimote in the roof, and you can use that to easily like track how far the robot has moved, so you can do it like more low cost than a motion capture system. So that was my content, so thank you. And
Wow.
I'll be happy to answer questions.
Yeah, questions.
I think you mentioned that you optimize also the geometry of the legs. Do you do that only to weight as objective, or do you also have other?
For that one, currently we are, so the question was if we are optimizing the geometry of the legs and what are the objectives for that. So currently we are only measuring the total weight of the robot. It's like calculating that. And the geometries are like we can change the length, and we also change angles in the joints and so on. But we like they're always cylinder shapes at the moment. But that's somewhere we really want to go to kind of further optimize the geometry of each single body part in a way. And it's like possible if you saw this then 3D art, you can like use that kind of formulas to make new shapes.
I was wondering, since the small and big robots had a lot in common in a way, like the insect-shaped in a way with how the legs and body is formed, if the evolution was going quite much longer, would it generate possibly completely different forms? Does it have the potential already?
Good question. So they look a bit similar. And that's because it's kind of restricted by our kind of design framework in a way. So it's what we call like a generative encoding. So that's basically it's always symmetrical, and there are like some genes specifying then like how many joints you have and so on, and then there's like some gene specifying then how many segments you have, and then there can be some variations in length and so on along the body. So if we let it completely loose, then we can start to see really like big robots coming up, but they're not so realistic for making them later. And in order to see like totally different shapes, then we would need to kind of open up a little bit on the freedom in the kind of generative process. Of course, that comes with a disadvantage as well, because then like the possibilities are so much bigger, and there is kind of more things to test. So to kind of explore very well, then you would need to kind of have even bigger populations, and you risk kind of getting stuck somewhere and not exploring enough. So you always kind of help a little bit to kind of restricting your search also.
Could you grow robots together so you'd have like ones that preyed on little ones, maybe, I don't know, like adding more parameters so you can like go in ways you're not expecting, like you'd end up with dinosaur-sized ones and tiny ones, like cohabiting?
Yeah, you could do that, and there's been some experiments on that using purely virtual robots. Yeah.
Anyone else? Okay, Kyrre, thank you very much. This is really interesting to hear your story. Thank you.